The equilibrium constant is given the value or the symbol of K. It tells us the relative concentration of the reactants to the concentration of products at equilibrium. We said last time that the concentration of products and reactants are fixed, it's constant and does not change. So what is the ratio of these concentrations? So let's say we have a reaction in which A and B turns into the products C and D. In the balanced equation, these small letters A, B, C, and D, it's the coefficients of the reaction. So we have the lowercase a, lowercase b, lowercase c, and lowercase d as coefficients. In our balanced equation, if I were to write an equilibrium constant expression, I would say this is called the equilibrium constant expression. I will start by writing the equilibrium constant. It's K, and the subscript here is C, because I'm talking about concentrations. In our equilibrium constant expression, what I'll say that Kc is equal to, in the numerator, I have the concentration of my two products. So I have C, and it is to the power of the coefficient, which is the lowercase c. So every concentration is raised to the power of the coefficient. So C, and don't forget it's D, multiplied by, not addition. So here is addition, but here in the equation I will write multiplied by to the power of d lowercase d, which is the second product. And in the denominator, I will have the concentration of the two reactants. So the first reactant is A raised to the power of its coefficient lowercase a, and B raised to the power of its coefficient lowercase b. So each concentration is raised to the power of the coefficient in the balanced equation. And it's important to stress that the concentration that we will be writing into our equilibrium constant concentration, this is called the equilibrium constant equation, are the concentrations at equilibrium. So if you started the reaction and you have the concentrations before the reaction has reached the equilibrium, you cannot use these concentrations. You can only use the concentrations at equilibrium. We get a value for the equilibrium constant, which is equal to K, and K is a constant for a particular reaction at a fixed temperature. So let's write an equilibrium constant expression for the following reaction, which shows the synthesis of ammonia. This equation shows us how ammonia NH3 is made from nitrogen and hydrogen. Everything here is in gaseous state. So I'll start by writing my equilibrium constant. What is my equilibrium constant? So I will say Kc. Let's write this. Kc is equal to the concentration of the products. Because I'm dealing with concentrations here, I will write the concentration of the reactants and products, and I will start with the product. What is my product? My product is ammonia. So I will write here the concentration of ammonia. And how do I write the concentration of ammonia? By writing NH3 between these two solid brackets. And since the coefficient of ammonia is 2, so I will write it here to the power of 2. And this is my only product, so that's the only thing which is available in the numerator. And then in the denominator, I'll have the concentration of nitrogen. And since the coefficient here is 1 in the balanced equation, I don't see it, but it should be 1. And we don't write 1 here in chemistry, so it's N2 to the power of 1. And then, if we remember, we said multiplied, not product, multiplied, not addition, of hydrogen gas concentration to the power of 3. Why it's to the power of 3? Because the coefficient in the equation, in the balanced equation here, was 3. So I will write H2 to the power of 3. We raise the concentration of hydrogen to the third power, For gases, it's more convenient to use partial pressures instead of measuring concentrations. So if we said that A and B and C and D are all gases, or in the same equation that we have used here, and instead of using concentrations, we use gases, I can say that equilibrium constant, which is Kp, this time because I'm talking about partial pressure of gases, is equal to the partial pressure of gas C. Again, I'm starting with the products, and to the power of C lowercase, which is my coefficient, and here I don't put the solid brackets because there is no concentrations, multiplied by the pressure, partial pressure of D, the second product, to the power of its coefficient D, lowercase, and then I will divide this by the reactant. So the reactant is the pressure of A to the power of lowercase a multiplied by the pressure of B to the lowercase of to the power of lowercase b, which is the coefficient. So if we go back to our reaction in which everything was in gaseous state, I can say that the equilibrium constant of P, because it's pressure for the gases, is the pressure of ammonia gas to the power of 2, because the coefficient here is 2, divided by the pressure, the partial pressure of the nitrogen, so divided by the partial pressure of the nitrogen, and nitrogen will be to the power of 1. So I will write it here as P. So I will write it here as P to N to gas, and then I multiplied by the pressure of hydrogen gas to the power of 3. Take care if you have an equation in which there is a solid or a liquid, pure solids or pure liquids are not mentioned in the equation. Only if you have aqueous or aqueous solutions or gases, you will use them in the numerator and denominator. But for example, if you have here, calcium carbonate solid that forms calcium oxide solid plus carbon dioxide gas. So the only thing that you will write in your Kp equation is the pressure of the carbon dioxide gas. That's the only thing that is you are going to write. If you have H2O liquid breaks down into H plus aqueous ions and OH minus ions, so the only thing that you write in the K equilibrium or the Kc is your concentration of H plus multiplied by the concentration of OH minus, and there is no mention for the liquid water. Now let's talk about our reaction quotient. And what is our reaction quotient, which has a symbol of Q? The reaction quotient that has the symbol of Q is just an expression which has the same form as equilibrium constant expression. So it is again the products to the power of their, so the products to the power of their coefficients divided by the reactants divided by the reactants again to the power of their coefficients. So Q is equal to the same equation, we'll use the same equation that we have used with the with the K constant of equilibrium. The Q tells us the relative concentration of the reactants and products at any point of time. So it's not necessary that I am talking about the equilibrium. If you remember, we said if you have Kc or Kp, the concentration and the partial pressure of gases that you are talking about is at equilibrium, is at the point of equilibrium. What if you make this equation, and when you make this equation, you don't have the values at equilibrium, have it at any point of the reaction which is not at equilibrium, then this will not be equal to K, it will be equal to the Q. So let's go back to our action for the synthesis of ammonia. And from nitrogen gas and hydrogen gas, notice how the Kc expression has the same form as the Qc. So I will write here the KQC expression it will be equal to QC equal to the concentration of NH3 squared divided by the concentration of N2 to the power of 1 multiplied by H2 to the power of 3. It is the same thing exactly here. The QC expression is the same as the KC expression. The difference is that for the KC expression, we have all our concentrations at equilibrium concentrations. And here in the QC, the concentration of nitrogen and hydrogen and ammonia is at any point which is not necessarily the equilibrium time. So the moment in time might be at equilibrium or might not be at equilibrium. If QC is equal to KC, then the point that you are asking about is equilibrium. If QC is equal to KC and you have said what is the concentrations now, then it is the point of equilibrium. While if the Q is bigger than K, or the Q is less than K, then this is not equilibrium. This is either reaction going in a forward rate faster than the backward rate, or the backward rate is faster than the forward rate. In the next videos, we'll be taking some examples to understand more about the QC and the KC and the equilibrium constant and the equilibrium quotient, or what we mean the reaction quotient, which is equal to products over reactants, the same way it is for the KC and KP. But as we said, this is not at equilibrium, any point of the reaction, while here this is at equilibrium. These two are at equilibrium, either concentrations or either partial pressures.